All right, the last part, heat. The idea of heat. Okay, bonds, when you talk about a solid, bonds will hold the molecules together. Okay, bonds will hold these molecules together. They will hold them in a fixed location. So we have bonds that hold things in a fixed location. The solid discs that you have here, your calculator, you have bonds that hold these things together. Okay? As thermal energy is added, okay, you add thermal energy to a solid. Okay? If you add thermal energy to an ice cube will turn into water because you're adding heat and thermal energy into that. So what is happening is you're adding energy into a system. When you add thermal energy into a system, into a solid, the potential energy increases. Okay, the potential energy increases until the points where the bonds can't hold the molecules in a fixed location anymore. Okay? So you're going to be held in a fixed location, but the potential energy continues to increase. And at some point, that potential energy, the bonds can't hold on because there's so much energy there. And bonds can't hold in a fixed position. If you have water molecules, ice molecules that are here, they're vibrating back and forth, the potential energy is getting stronger and stronger and stronger, and finally the bonds break. And the molecules start to move around a little bit. Okay, they start to get more mobility to them. Well, that is a solid that is turning into a liquid. Because all of a sudden these molecules, rather than being in a fixed position, vibrating back and forth and all this potential energy, break apart and the molecules start to be able to move around. And you start turning ice into water because the molecules will move around. It'll become a liquid. So your potential energy, as you increase this thermal energy into a solid, potential energy will increase until you can't hold it anymore. Then it turns into, the bonds break, and it turns into more of a kinetic energy. Okay, once again, temperature is your average kinetic energy. Okay, your average of your kinetic energy is your temperature. So what is happening is you have this kinetic energy that is increasing. You have potential energy increases until the molecules break, or the bonds break, and then all of a sudden you start having movement. Once you start having more movement, you're going to have more kinetic energy. If you have more kinetic energy, that means your average kinetic energy is going to increase. If your average kinetic energy is going to increase, that means your temperature increases. Okay, so they all run hand in hand in regards to when you look at a solid and you convert it into potential energy to break the bonds, to turn it into a liquid, you have then an increase, a less of a potential energy because you're now converting the potential energy into kinetic energy because the objects are starting to move. Just like the roller coaster ride. You have the roller coaster ride, you have a potential energy at the top of a hill, converts itself into kinetic energy because the objects start moving a little faster. Potential energy decreases, kinetic energy increases. Same idea here. At this point, the solid becomes a liquid. potential energy is increased, not the kinetic energy. If the kinetic energy is increased, then temperature is not. If the potential energy, kinetic energy, if the kinetic energy is not increased, then the temperature is not increased. Okay, so you have this potential energy that breaks the bonds. Okay, potential energy that breaks the bonds. That potential energy breaks the bonds that take it from a solid into a liquid. And then we start adding kinetic energy. It converts more into kinetic energy because it's going to have more movement. So during the process of just the breaking of the bonds, the breaking of the bonds is the increase in potential energy till the bonds break. So the melting process, during that actual melting process, right at that point where it goes from a solid to a liquid, that's all potential energy. As it becomes more of a liquid, the kinetic energy will start to increase. Once again, this process, the solid becomes a liquid, is a potential energy process until we start adding more kinetic energy to increase the temperature. Which tells us ice at 0 degrees Celsius, which is freezing, turns into water at 0 degrees Celsius. There's no increase in temperature or kinetic energy during the melting process. All the thermal energy is then used to increase the potential energy to break the bonds. The melting process is the breaking of the bonds. And this potential energy increase breaks the bonds and turns us into a melting process. The bond breaking is melting. The bond breaking occurs when you increase the potential energy to a point where it just can't hold anymore. And the bonds break, we become a liquid, and then we can start increasing the temperature at that point with that kinetic energy. So potential energy is the melting process. This thermal energy increases that potential energy to break those bonds. We melt the process. We have a melting process. Ice at 0 degrees, once again, a solid will turn into a liquid at the exact same temperature. Ice at 0 degrees Celsius will turn into water at 0 degrees Celsius when we melt. So we then talk about the heat of fusion. It's the amount of energy required to melt a mass of ice or mass of a solid. This is sometimes referred to as the latent heat of fusion. It's the amount of energy required to melt a unit mass of a solid. Sometimes it's called the latent heat of fusion. Units are joules per kilogram. We don't have to worry about the delta T or Celsius in there because you have 1 kilogram of ice turns into 1 kilogram of water at 0 degrees Celsius. So we go from 0 to 0. So I have no delta T in there. The latent heat of fusion for ice is 3.34 times 10 to the 5th joules per kilogram. That means for us to melt 1 kilogram of ice, it takes 3.34 times 10 to the fifth joules. Now, if you think back to what we were talking about yesterday with the specific heats, the specific heats we're dealing with was 200, 300, 400, maybe 1,000. Okay, if we take a look at this, this is 334,000 joules of heat to melt 1 kilogram of ice. Which is a lot compared to what, you look at our specific heats to raise metal, some of the specific heats we had there, so even water, to get 1 kilogram of water to increase by 1 degree Celsius, it took 4,180 joules of heat. Okay, 4,000. This is 10 times the amount of heat to melt a kilogram of ice. Five kilograms of ice at 0 degrees Celsius becomes 5 kilograms of water at 0 degrees Celsius. And the key thing to remember, the energy added is only changing your state. It is not changing the temperature. Your energy added is only changing the state. It's going from a solid into a liquid. But once again, I'm maintaining the temperature. We can also have latent heat of vaporization. It vaporizes things. It turns from a liquid into a gas, same process. The amount of thermal energy required to vaporize a unit mass of liquid is sometimes referred to as the latent heat of vaporization. And for water, to vaporize a kilogram of water, it's even more than to melt a kilogram of ice. To vaporize water, it takes 2,226,000 joules of heat to vaporize water, a kilogram of water. Compared to what we were just talking about, vapors and melting, it was only 334,000. We have now over 2 million joules of heat. It is easier to melt ice than it is to vaporize ice. Or vaporized water. Q is the amount of heat required to melt a mass, M, and how we calculate this amount of heat to melt is your heat of fusion times your mass. And likewise with vaporization, the amount of heat to vaporize the mass is the heat of vaporization times the mass. Again, two more things to add to your equation sheet. We have 396.67 grams this is beaker and water. We'll let it get to a temperature here. Throw my thermometer in there. I'm looking for thermal equilibrium between the thermometer and the. I'll make this even better. A little bit more thermal. We have a calorimeter cup. Which is 61.16 grams. We got water at 224. No. We got water at 23 degrees Celsius.
So that means you broke. You broke? Yes. But my life, I would break my foot. I'm sure I did. That's all I did.
I'm going to throw some, we have water at 73 degrees. I'm going to pour some water into here, into the calorimeter cup. Which is 223.62. So we have cup and water is 223.62. And then I'm going to throw some ice in there. Stuff this down in here. Try to isolate that as best as possible. And what's going to happen to the ice? It's going to melt. All right. So let's take a look at a problem here. How much heat is required to take ice at -3 degrees Celsius to water vapor at 110 degrees Celsius? Now, what you have to realize is whatever the outside environment temperature is, all bodies are going to assume that temperature. Okay, so if it is -10 degrees Fahrenheit outside, that means all objects outside are going to look to assume that -10 degrees Celsius. Your car, if it's out there, any objects that's sitting out there is going to assume that also. So if you have ice that's out there at -10 degrees Celsius, that means the ice is going to be -10 degrees Celsius. Okay? So what we have here is we have ice at -3 degrees Celsius. We want to figure out how much heat it takes to change this ice into water vapor at 110 degrees Celsius. Well, the process that we have to go through first is we have to take this from ice at -3 degrees Celsius to water, or to ice at 0 degrees Celsius. So we have to do a MC delta T to take it from 0, from -3 to 0. Well, the mass that we're talking about here, let's keep this simple. We'll take it 2 kilograms. We'll use that as our mass. So we have 2 kilograms. What is our C for ice? 2060 joules per kilogram Kelvin or Celsius. And then we have a delta T here. Our delta T is final minus initial. We have final temperature minus initial temperature, so this turns into 3 degrees. So we have 2 times 2060 times the value of 3. So how many joules of heat do we need? 12,360 joules of heat. Then we need to take ice at 0 degrees Celsius to water at 0 degrees Celsius. So we have to now melt from ice to water. So how we melt from ice to water, we have heat of fusion times our mass. Well, we just talked about, this is 3.34 times 10 to the 5th. times our mass of 2 kilograms. So we have 6.68 times 10 to the 5th joules. Then from here we have to do water from 0 degrees Celsius to 100 degrees Celsius. So we go back to our MC delta T. So our mass is still 2. Our C is now 4180. So 4180 for water. Times our delta T, which is T final, 100 minus 0.
Who's gonna look ahead?
Hmm?
The final. That's what.
Because when it's 100, what's it have to do? What's water do at 110?
Oh, it vaporizes.
It vaporizes. Goes into a boiling.
What's water vapor? C for water vapor.
I'm looking at it right now. $19.96.
You add all those numbers up then.
And then you'll have to add all those numbers up.
Big number. 52,768,000.
200 and what?
No, going from
What do we have for 100? Let's see.
No, I did it. So that's, no, you're way lower. Yeah. I was No, I think you're right, Tristan. I think I might have went too far. Dallas.
We have 12,360, then we have 6.68 times 10 to the fifth. 836,000 for the water from 0 to 100. Then 4.52 times 10 to 6 for vaporizing, and then 39,920.
I was way off. I missed a zero or something. It's 6,076,280.
We go with that. Okay, once again, organizational skills and organization, we get through that.
A lot of tools.
Yep. Let's see. 220 grams of water, negative 10 degrees Celsius. Is added to 400 grams of water at 50 degrees Celsius in the Yeti. Ice, baby. Ice, baby. So you're putting ice at negative 10 degrees Celsius added to 400 grams of water at 50 degrees Celsius, the Yeti enclosed up. After the ice melts, what's the final temperature of the water?
Water is.
So you have water, 400 grams, 50 degrees Celsius, and you have 20 grams of ice at negative 10 degrees Celsius. So now you're in a Yeti, which means everything's going to be conserved. What is lost by one is going to be gained by the other. So if I add up all my heats, they should all add up to 0, because my conservation of thermal energy is going to occur here. What's lost by one is gained by the other. So we had to take a look at ice from -10 to 0, and then turn this into water.
What is the joules per?
So we have 0 to some final temperature. So you have to take a look at ice from -10 to 0, and then you have to take water from 0, and this is 20 grams of ice from -10 to 0, and then that's going to turn into water. It's going to go from 0 to a final temperature. And then you also have water, which is going to be going from an initial temperature of 50 degrees Celsius down to a final temperature. Don't know what the final temperature is. So we have ice. We have ice here, which is 20 grams. We have an MC delta T with this added to the heat of fusion times mass. And then when it turns into water, we have an MC delta T here. So we have 3 phases with the ice. And then just with the water by itself, we have an MC delta T here. When we add all these up, these should add up to a value of 0. So we have our 20, our 20, and our 20 here, and then over here, this is our 400. Now my MC delta T, we have to take it up to 0 degrees. So we have final, which is 0. T final, which is 0 minus 10, minus a -10. But then we have to take it through fusion. So we have the 3.34 times 10 to the 5th times this value of 20. And then when I go to my third phase, I got 20 times 4180. And then we have a T final minus our T initial, which is 0. I guess let me take a look at this. If I keep everything in grams, I know our units are in kilograms. I should probably change this all to kilograms. So we have a 0.02. 0.02. I don't think it will matter. 0.02 there. Okay, what I'm going to do is okay, we have melted everything. I'm going to give cup water and ice mass. First of all, I'm going to take a look at the temperature. Seven degrees Celsius.
gotta get through fusion, and then water.
41.
You gotta
Tell me these words, they mean
It's actually 46. That makes more sense. 46.1.
anything.
45.9.
See if you can finish that out. We'll work on that Monday, and we'll look at what I did, the little experiment I did up here also on Monday.